We are Group 5 and our topic is air stripping method. So first of all, we should learn about what is physical mechanism of air stripping method. So let's take a look what is air stripping method first. In general, air stripping is the transferring of volatile components of a liquid into an airstream. It is an environmental engineering technology used for the purification of groundwaters and wastewaters containing volatile compounds. Then we will take a look how air stripping method works. The key part of air stripping method is changing chemicals from liquid to gas. Specifically, air stripping removes chemicals called volatile organic compounds, or VOCs. VOCs are chemicals that easily evaporate, which means they can change from a liquid to a vapor or a gas very easily and quickly. The air passing through the contaminated water helps evaporate VOCs faster. After treating the water, the air and chemicals vapors are collected, and then vapors are either removed or vented outside if VOC levels are low enough. Air stripping is commonly used to treat groundwater as part of pump and treat cleanup method. Now, with the preparation above, we can talk about the most important part of physical mechanism, the process description. The process consists of countercurrent flow of water and air through a packing material. The packed tower consists of cylinder drum equipped with gas inlet and distributing space at the bottom, a liquid inlet and distributor at the top, gas and liquid outlet at the top and bottom respectively, and a supported mass of inert solid shape called tower packing. In the traditional system, water is pumped to the top of tower and is allowed to flow down over the inert packing, while the air is pumped countercurrent from the bottom of the tower. The contaminants of interest, such as ammonia or volatile organic compounds, VOC, are stripped out of the water into the airstream. In the practice, two methods are used to achieve contact between two phases, so that match transfer can occur. So the first one is continuous contact, and the second one is staged contact. Different flow patterns used in the practice include countercurrent, concurrent, and cross-flow. The most common flow pattern is countercurrent mode. Therefore, what is the difference between different types of flow pattern in air stripping method? As figures shown above, concurrent flow is the flow in which both fluid streams enter the equipment in the same direction. Whereas in the countercurrent flow, the streams enter at opposite ends of the equipment. In application of air stripping method, the countercurrent flow patterns are more efficient than other two. So that's why countercurrent flow is the most common pattern in air stripping method. Then let's take a look at a short cartoon video. This video builds a basic model of air stripping method and describes the basic idea of physical mechanism of this method.
As the stripping medium contacts the impure product, the lighter impurities begin to diffuse from the distillate into the stripping medium. The impurities are drawn off through the top nozzle and routed back into the larger fractionator column.
When air stripping is used correctly, it can be very effective. However, you must know when to use it and when not to use it. To determine this, you need to look at some factors. The first one is to look at the volatility of the contaminants themselves. Next, you have to determine types of the concentration you are dealing with. Finally, you want to look at the properties of the water in the aquifer. This also affects the efficiency of your system. First, let's look at the characteristics of the contaminants. Volatility is an important factor to determine whether gas stripping is suitable for remediation. In the air stripping process, you are basically trying to convert the liquid phase of the contaminants into the gas phase of the contaminants. To determine if you are going to get this transfer, you have to look at the volatility of the compound. Volatility refers to the tendency of the contaminants to vaporize into gas phase from liquid phase. The more volatile it is, the easier it is to change from liquid phase to gas phase. Air stripping is usually effective in removing volatile organic compounds. Volatile organic compounds are organic chemicals with high vapor pressure at room temperature. There are different kinds, for example, very volatile compounds and semi-volatile compounds. With high volatile VOC compounds, high air stripping efficiency would be. If VOC compounds are semi-volatile, you may need to provide heat to get contaminants into the gas phase with greater efficiency. Therefore, you may want to consider this when deciding whether to use air stripping. Volatile organic compounds are common substances in the gasolines and solvents, so there are still a lot of volatile organic compounds in the environmental contamination. Air stripping is ineffective for inorganic contaminants. When you want to know if air stripping is effective at removing certain contaminants, you can look at Henry's law constant. On the right side of this slide, you can see the definition of Henry's law. The Henry's law constant is a key important parameter for determining a chemical's environmental distribution behavior. It reflects the relative volatility of the particular substance. It is used to determine whether air stripping will be effective. Chemical substances with high Henry's law constant values will volatilize from water into air and be distributed over a large area. Chemical substances with low Henry's law constant value tend to persist in water and may be absorbed onto soil or sediment. In general, organic compounds with constant of more than 0.01 atmospheres cubic meters per mole are considered to be susceptible to stripping. Several compounds have been successfully separated from water using air stripping, including chloroethylene, TCE, DCE, and PCE, etc. The following table shows some estimates of values of Henry's law constants for some common volatile organic compounds. As you can see, it depends on temperature. These numbers appear to be conservative and could be used for design. Henry's law constant and hydraulic stability of the column will help determine the air over water ratio. That is defined as ratio of the volumetric air flow to the volumetric water flow. The recommended value of the air to water ratio varies with these two factors. Considerations of whether off-gas treatment will be required also affect the selection of the design air-over-water ratio, since large air volumes will be significantly more expensive to handle in an off-gas treatment unit. The air-to-water ratio is related to the stripping factor S by the following equation. Normally, stripping factors of between 10 and 15 work well in cases where no off-gas treatment is required, so that as an initial guess, one can use to estimate the air-to-water ratio needed for the column. This guideline works well to components like trichloroethylene and BTX. It should not be used strictly for components that have Henry's constants below 100 since it would yield unreasonably high values of air-to-water ratio. Typically, as the ratio increases, efficiency will increase until a point of flooding is reached. Next, a common problem with the use of airstripping is that removing VOC to very low levels, such as less than 0.5 parts per billion, would be difficult without paying attention to the detailed design and layout of the airstripping. Very slight defects in the gas and liquid distribution can cause the stripper to not work properly. This also affects the efficiency of airstripping. The best way to ensure proper operation at such low level is to ensure that the gas is distributed properly at the bottom of the tower. In airstripping system, paradoxically, the high mass transfer efficiency of the stripper promoted the deposition of insoluble metal oxides and the growth of bacteria. High surface will be more effective, but will also promote fouling. If the contaminated water contains free iron or other minerals, the action of stripping air may cause some of these compounds to precipitate and contaminate the packaging medium. Organic contaminants promote biological growth and aggravate the pollution problem. And if the water is not pre-treated before entering the tower, the air stripper will eventually lose some of its efficiency and capacity due to contamination.
Hello, and next is field implementation. There's a few things to consider when choosing an air stripper and what kind. The first is, does the pollutant have a relatively high vapor pressure and low aqueous solubility? If so, perfect. As discussed from earlier, pollutants with a relatively high Henry's law coefficient can be economically stripped from water. For example, benzene, toluene, xylene, which is found in gasoline. Ammonia can also be stripped, which is commonly found in wastewaters. So next is the project at hand short-term or long-term? This will affect if you want a packed column or low-profile air stripper. Some variables to consider that will affect the timeline is, are the contaminant concentrations high? What is the amount of water needed to be treated? Can the groundwater be pumped at a fast rate? And will there be buildup of any mineral deposits or algae on the packing material? This will frequently require removal and cleaning. These factors will, of course, vary site to site. Next is, will the gases released be harmful, and will further purification need to be done? For example, as air is coming up through the bottom of the low-profile air stripper or packed column, it will, of course, collect those contaminants, and then they'll be released into the atmosphere. So will those need to be filtered? Those are commonly done with a carbon absorption system, which is usually most used in the field, or a catalytic oxidation, which is another option. So in the next couple slides, we'll discuss whether to use the packed column or low profile air stripper and the difference between them and why they're important. The packed column air stripper is among the most common because of its efficiency. So it works by water coming in here, getting pumped all the way to the top of the column. This is closely monitored on the inlet of both the water and the air because you have to have a perfect ratio or this whole process is not going to work. This air stripper right here is commonly full of little discs or balls which are made of plastic, steel, or some ceramic packing material to maximize the air to water contact. So once the water reaches the bottom, hopefully it is clean by this point, but if it's not, some variations of this design is it would go from this collection tank back into the feed tank and then run this process in a loop. So also some other variations would be this heater and this heater. Sometimes the process doesn't even need a heater and it can be successfully ran, but if it cannot, that's why it is in there. So some considerations for the column right here is when designing the tower, there are certain design criteria that needs to be considered. This would include the surface area provided by the packing, the column height and diameter, and then also the air-to-water flow rates. Designers of the air strippers want to obtain the largest air-to-water surface contact in order to reach maximum efficiency of removing contaminants. Some other things. Pack strippers are also work more efficiently at removing lower volatile organic compounds than tray strippers. Furthermore, packed tower strippers are more cost effective than tray strippers when treating large quantities of water. Keyword large quantities. And then also I said lower volatile organic compounds. That's because, again, because they're packed in so tightly through this column, it's very, very efficient, which then is able to filter out some substances that are closer to the properties of water. So next is low profile air strippers. And these are more cost effective at treating low quantities of water compared to packed column air strippers. These are used in a variety of applications, including municipal drinking water treatment, groundwater remediation, industrial processes, and wastewater treatment. These can be easily brought to the contaminant site instead of trucking the contaminant elsewhere. Or if it was a large project, then of course you could build your own packed column air stripper, but that's not always feasible. So you can see right here, like these are actually clips right here along these trays, and that's what makes it so portable. Is you can literally put these in any single trailer and bring it right to your destination. So it works by kind of the same as before, but water drops in through the top, but then it goes back and forth over these trays instead of constantly going down through materials. And then you can see these trays are perforated just the right amount, though, that the flow rate from this air pump right here, when it comes up, it bubbles through the water instead of the water passing through. It forces the water to still take the route along the trays. Finally, there is a sump pump right here, which sucks the water out as the level rises. It is maintained by a float, and this, again, just the same as before, this can be put in again, or hopefully the water is clean enough that by that point that you can run it to surface water or something like that. Continuing on with low profile air strippers, a company found was Carbon Air. So they make many different quick and easy variations, and this gets you up and running very quickly because before I explained that these are literally just clipped on these trays. So yes, they can be made custom for your application, but most of the times they can have a generic version. For example, they have these models right here, which vary from a 16-gallon capacity all the way up to 1,000 gallons. So as discussed earlier, a packed column air stripper is always going to be more efficient, and it can handle larger quantities of water. But these things are great that they're cheaper and they get up and running faster. And if you're not doing a lot of purification, then these are commonly easier to deal with. So at this point, I'm going to pass it on to John for him to continue.
Continuing on with the demonstration level, I am John Groover, and I am going to be talking about a few case studies implementing air stripping. The first case I will be introducing is ammonia nitrogen removal and recovery from acetylene purification wastewater. As it was said in the title, the contaminant trying to be removed is ammonia nitrogen. The source is from acetylene purification wastewater produced during this production of PVC materials. This wastewater contains large amounts of ammonia nitrogen NH4N, typically in the range of 100 to 200 milligrams per liter, and flows into nearby waterways, causing harm on the environment. Because nitrogen is an important element to living things, it will be recovered, and the goal will be to treat and recover the NH4N in the wastewater before it reaches the waterways. In this method, it can be seen in Formula 1 that when NaOH, an acid, is added to the wastewater, the non-volatile ammonium ions NH4+, convert to volatile ammonium molecules NH3. The NH3 aqueous solution can be then stripped from the water phase by the addition of the air, which can be seen here. Once in the gas phase, the NH3 which can be seen in Formula 2, is added to an H2SO4 acid solution to be absorbed. Now, some things that were needed to be considered before an experiment was conducted was the initial pH of acetylene purification wastewater, APW, the airflow rate, APW temperature, and stripping time. These variables would affect recovery percentages and effectiveness. The first variable examined is initial pH. pH is one of the most important factors in controlling the air stripping process. In the figure below, it can be seen that there are two graphs, one showing stripping time versus removal efficiency, and the other stripping time versus negative ln Ct over Ca, which is on the right which represents the liquid phase concentrations of NH4N. The legend located here at the bottom shows the initial pHs of 10 in the square, 11 as a circle, and 12 as a triangle. From these experiments, it shows the optimal pH of 12 is used, as has the best removal efficiency. The second variable examined was airflow rate. This is an important factor as increasing or decreasing the flow determines the rate at which NH3 can be removed. In the figures below, you can see the different removal efficiencies at different airflow rates. For example, the slowest airflow rate of 0.375, represented as the square, shows that at a lower airflow rate, the removal efficiency is not as high compared to any other flow rate, such as 0.500, 0.625, or even 0.750. The rate they chose in this situation was 0.500 meters cubed HL. This was due to the possible of overflow going any higher. Now, the final variable examined before a design can be constructed is the ammonia purification wastewater's temperature. In the two graphs below, it can be seen that the KLA, overall volumetric mass transfer coefficient, and the removal efficiencies at 30 degrees Celsius are much lower than that of 60 degrees. Because of the effectiveness of the 60 degrees Celsius, that was the temperature chosen. So after their investigation, they found the optimal conditions of the experiment should be APW initial pH of 12, an airflow rate of 0.500, an APW temperature of 60 degrees, and finally an air stripping time of 120 minutes. With these conditions, the lab experiment was able to achieve removal efficiencies of 91% and a residual concentration of 12 milligrams per liter. A 93% absorbent percentage was also achieved. To achieve these end results, an experimental setup was needed, which is shown here on the right. As this is an experimental setup, there is no pump for the liquid contaminant as it is poured in. And in this case, it was 0.4 liters. The temperature probe would read the temperature and adjust the heater to the temperature that was optimal, which was 60 degrees Celsius. Once this was accomplished, the air blower will start at a rate of 0.500 for 120 minutes while the condenser collects the NH3 gas and sends it to the absorption unit where the NH3 gas will mix with the H2SO4 solution where it will be absorbed. The second case that will be assessed in this treatment is carbon absorption and air stripping removal of MTBE from river water. First, this is a lab experiment from Renew, Nevada, and it's from the Truckee River. The contaminant is methyl tertiary butyl ether, or MTBE for short. It is shown here on the right. It was used for fuel oxygenates in reduction of carbon monoxide CO and ozone O3. The goal of this treatment was to reduce MTBE to safe limits and to analyze different air-water ratios to determine best results. On this slide, you will see the following table comparing different air-to-water ratios. It shows distilled deionized water as a control with MTBE bot, while the river water is a raw sample. As you can see, there is a direct correlation between the air-to-water ratio. As the ratio increases, the greater the removal percentage is. A negative effect of this would be the increase of airflow would cost much more, which will be discussed later. Now for the design experiment. Another success of air stripping is that it can be used with other treatment methods, as seen in Figure 1. Here, GAC is used, which is granulated activated carbon. It is used as a pre-treatment, and this will help with the overall removal of impurities that the stripper cannot handle. Once the house air runs through the GAC to remove the unwanted materials, it will proceed to the flow meter where the desired air-to-water ratio is chosen. This is also true for the 50-liter carboy, where the pump will push the desired ratio to the air stripper column. In Figure 2, the specifications for the system can be seen. Later, you will see how these specifications affect the cost of the project, but for now, on to applicability and limitations.
In certain aspects, and it has defects and limitations. In terms of application, the air stripping method has high VOC removal efficiency. At the same time, the air stripping equipment can provide long-term reliable use time within the service life. The equipment can be moved and built in a suitable location. On the other hand, the disadvantages of air stripping method is also obvious. First, it cannot handle all types of pollution. And secondly, when the water quality does not meet the standard, it will cause blockage and cannot be used. The gas emit based on the principle of the equipment needs to be treated as well. The packed column and low-profile air strippers can capable of removing more than 99% of most VOC contaminants. This table shows the data at Rockaway air stripping equipment VOC removal efficiency. We can find that all VOC removal efficiency reach 99.99%. Increasing the depth of packing or the number of trays will increase the stripping. Increasing the airflow through a packed column may increase the efficiency. However, increasing the airflow beyond a certain point will cause the flood. The second advantage for airstripping technology is reliability and availability during the lifespan. The airstripping device can work stably for a long time when the water meeting the conditions. No functional problem encountered during the demonstration. The system was operational approximately for 19% of all available time. The table shows the airstripping system working and the maintenance process in half a year. We can find that only less than 1 month the system was during the maintenance process, but it can functional for other 5 months. The airstripping method needs a site. The airstripping device can be transported or constructed on the site easily, and the device occupies a small area. But at the same time, the device requires additional power supply, monitor ponds, and gas treatment device for operation. As we mentioned before, if the pipes blockage or more gas added into the tank, the flood will happen. So we need a monitor agency and monitor ponds to control the system safety and the effluent quality. As we mentioned before, the air stripping method is not suited for all contamination. The gas stripping method is only suitable for specific substances that meet Henry's law constant no more than 0.001 cubic meter atom per mole. It is only effective for small particles or volatile substance suspended and floating in the liquid, so that the air can take the targeted substance out. So if the substance heavier than we set, the substance will sediment at the bottom of the water and flow out to the effluent. The second important limitation for this technology is it can be folded when water with high hardness, low pH, or high microorganism concentration. Air strippers frequently become folded by mineral deposits when calcium exceeds 40 mg per liter, iron exceeds 0.3 mg per liter, and the magnesium exceeds 10 mg per liter, or from biological growth, which water has high microorganism concentration. Air strippers may become plugged with a solid that must be removed. Packed column air strippers must either have the packing removed for cleaning, or the packing must be washed with an acid solution. Both operations are time-consuming and costly. Low-profile air strippers are often desirable when folding is happening. Low-profile units are often fastened together, tray by tray. Small units can easily be disassembled to physically remove the biological or mineral deposit. Larger units have access ports on the side of each tray for cleaning with a high-pressure water spray. Pre-treatment of water prior to stripping is often required. When the system facing the bad water quality, it will take more time to maintain the system and cost more. The air stripping is not a solution to the pollution in the water. The air stripping method can only transfer the contaminants from one medium to another. After the pollutants are transferred to the gas, we can't directly discharge the waste gas as well. So, active carbon and thermal oxidation are common used to treat the off-gas. The unit efficiency of either method is directly proportional to the concentration of the contaminant in the off-gas. Active carbon is simple, but it does not destroy the contaminant substance, and many result in potential disposal cost. Thermal oxidation destroys the contaminant, but is more complex during the process. So, air pollution control device should be evaluated before determining which device to use when we design the air stripping system. Also, that means the lower concentration of VOCs we want in the gas stream, the higher control cost we will need to pay in the system.
The next topic we will discuss involving gas stripping is its cost and availability. As spoken about before, gas strippers come in many forms. We will focus on two for this section of the presentation. First, we will discuss the cost of low-profile tray stackers. The three main cost drivers of this form of gas stripping are the influent flow rate, the relative contaminant vitality, or the relative dispersion of the contaminant, and then also, when necessary, the treatment of the effluent gas. The Federal Remediation Reference Guide breaks down the cost of a low-profile tray stack into 4 scenarios: A, B, C, and D. As you can see in the charts, A is small and easy scenario, and D is a large and difficult scenario, etc. With the increase in gallons treated, plants are able to perform air stripping at a much cheaper price. Second, we will discuss the cost of the form of gas strippers known as packed towers. Packed towers share the same 3 cost drivers as tray stackers. From the picture on the right, you can see the size of some existing packed towers. As before, the pricing is broken up into scenarios, as different costs will be seen in different sites. Packed towers are equal to or more expensive than low-profile tray stacks. The cost per gallon ranges from $0.0005 to $0.0025. The estimated cost shown in both of the forms of gas strippers used the same gallons treatment for each scenario, so the pricing can be compared. Packed towers in a small and difficult scenario are the most expensive option at $34 per 10,000 gallons treated, while both tray stacks and packed towers with easy and large scenarios are the cheapest at a cost of $4 per 10,000 gallons treated. From this data, it can be seen that both forms of gas strippers are comparably priced, and the choice of which to use in each future plant will require more specification requirements. That is the end of our presentation. Thank you for watching and good luck on the quiz. Please let us know if you have any more questions.